Okay, on to question 5, and this is a tricky one. The integral of ln of something. Now, take a look at your formula booklet. If you're not sure about how to integrate a particular function you've got. Here we go. We've got, well, ln doesn't appear there or there. Ln doesn't appear in our integral list of integrals here. So we need to know this one. Now, what we need to know for ln is a technique, and it's a very it's like a trick, and the trick is to represent it as a 1 times ln of x over 2. Clearly, ln of x over 2 is the same as 1 times ln of x over 2. By doing that, we've created a product, and when we're integrating products, we can use by parts. And when we use by parts, we have the different parts are going to be u, and then when we differentiate that, we get du by dx, which I call u dash, depends on who your teacher is. The other part of this is dv by dx, or v dash, and then you integrate that to get v. Incidentally, I should say that the integration by parts formula is in the formula booklet here, notice. So the integral of u dv by dx is equal to uv minus the integral of v du by dx. Okay, so that's in the formula booklet there, the integration by parts. So if you can create a product, or if you've got a product, then you can sometimes use integration by parts to help out with that. Let me just jot that formula down for you on here. Okay, now there's a little acronym which is LATE. Okay, a nice little acronym to help us remember what the order of priority is to let equal to u. So the bit that's equal to u in order of priority would be logs, bits of algebra, that is to say things like x squared or x cubed, trig functions, exponentials. So logs come first. Now here we've got a log, it's ln of x over 2, so that is then going to have to be our u. Okay, and our dv by dx will be the other bit, which in this case then is 1. Now, generating the other two parts here, we've got, so if you differentiate ln of x over 2, differentiate ln, you get 1 over, so 1 over x over 2, but then you've got the chain rule going on here as well, because the inside of this is x over 2, or a half x, that could be written as a half x. Differentiation of the inside function there is a half, so we're going to multiply that by a half. Okay. Now that all tidies up to actually just 1 over x, because 1 over x over 2 is the same as 2 over x times 2 over x by a half, and you get 1 over x. Just squeeze that in there. dv by dx equals 1. Integrate that to get v, and you get back up to x. Now normally that would be creating additional complexity in your second, on your right hand side of the integration here. But actually in this case, because the du by dx, the u dash bit here, is going to be 1 over x, that's going to sort of cancel out and make it quite a nice right hand side. Okay, putting all of that together then, so this was effectively, to make it clear, that was our u, that was our dv by dx, okay, from the left hand side there. So when we integrate, then we get u times v, so that is to say the ln of half x times by x, so I'll write that as x, ln of half x, minus the integral of v du by dx, so v du by dx, so an x times 1 over x, x times 1 over x is clearly just 1, and if we integrate 1 we get x. Okay, so we could finish there, or we could spot that x is a common factor and pull it out. And we could finish there instead. Okay, in part 2 we have integral of sine squared x, and we've already encountered two of these actually already in this homework. So if you're integrating either sine squared or cos squared, you have to use the double angle formula for cos. And the starting point for double angle for cos, you might remember, is cos 2x equals cos squared x minus sine squared x. Replace cos squared x with 1 minus sine squared x there, and you end up then with 1 minus 2 sine squared x. Okay. So call that version 1. Let's rearrange version 1. Add across the 2 sine squared x. Subtract across the cos 2x. And then finally divide by 2. I'm going to get a half minus a half cos 2x. Okay, so that then now is what we can substitute into here to help integrate it. So therefore, integral between pi over 4 and pi over 2 of sine squared x is actually equal to the integral between pi over 4 and pi over 2 of a half minus a half cos 2x. Okay, integrate a half, we get a half x. Integrate a half cos 2x. So the half is going to hang around. Integrate cos, we get back to sine. And I've already pointed that out in question 3b, if you need help with that. So integral of cos is sine. And because the inside function is linear there, 2x, we can apply the inverse chain rule. So therefore we divide by that 2. There, so I'm going to represent that as a half at the front there as well. Okay, so next step then is to, well, this can be a quarter, and at the same time I'm going to start substituting in my limits there. So a half brackets pi over 2 minus, so this is a quarter sine of 2 times pi over 2. A half times pi over 4 minus a quarter there, sine of 2 times pi over 4. Okay, tidy that up a bit. We've got pi over 4 there, minus a quarter sine of pi, so pi over 2 times 2 is pi. Over here we've got, sorry, that was a closed bucket there, so pi over 8 minus a quarter sine of pi over 2. Now, sine pi, you can check on your calculator, but that'll be 0. Sine pi over 2, check on your calculator, that should be 1. So we end up with pi over 4 minus pi over 8 plus a quarter times sine pi over 2, which is 1. So we're nearly there. Now a quarter pi minus an eighth pi, a quarter minus an eighth is an eighth. So that's giving us an eighth pi. A quarter times 1 is obviously a quarter. So 1/8 pi plus a quarter. That's where we finish.